Okay, so this pre-recorded lecture is intended to make up for the snow day we have on the today, which is the 23rd. Since it's been a few days since we last met, let me just remind you what we covered the last time we met on Wednesday. So let me just share the screen. All right, so hopefully you can see what I am seeing. All right, so last time we started in 1.1, and this is subsets of real numbers. So as I emphasized when we met, the two most fundamental and important concepts in all modern mathematics is that of a set and that of a function. And so we're going to look at sets first, and then in chapter 2, we're going to look at functions. Hold on. Something doesn't seem right. So hold on for a second. Sorry, I wasn't sure if it was picking up my audio. So hopefully it's actually picking up the audio. All right, let me share my screen again. All right, so yes, the two most important concepts in all modern mathematics is that of a set and that of a function. And we're going to look at sets first. And we're just going to use more or less a naive idea of a set, and it's just a collection of things, and that's sort of undefined, or maybe it's perhaps circular because of what it's a collection. But we're just going to work on and operate with an intuitive idea of a set. So just remind you, we looked at a few sets. So the first set, these are subsets. We're typically going to talk about sets of real numbers or subsets of real numbers. So we're going to single out a few of them, the few that are important. So this first one is n. This is the natural numbers, and this set you can just list. So these are the natural numbers, and so we have these braces right here. This denotes the set, and then right here we're listing the elements, and then these ellipses just indicate that this is a non-terminating sequence. So it's all the counting numbers. The set consists of all the counting numbers. And so the first two sets we're going to look at, one of which we already looked at, the natural numbers. You can actually just explicitly list the elements. So the next set is basically contains the natural numbers and all the negatives and zero. So we can, in a sense, in principle, list these numbers. And so these are the negatives, zero, and then the naturals. So these are called integers. And then the next set is the rational numbers. In this case, though, we can't actually list out the elements. So what we need is we don't have that luxury in this case. And that's actually true of a lot of different sets you encounter in mathematics. You can't explicitly list the elements. So we're going to need to set up some convention. So this is called set builder notation. So not always, let me just say that let me write down what I just said. So not always the case that we can explicitly list elements of a set. But often the case you have the elements that you're of the set that you're interested in have this common property. So often the elements you want to collect together have some common property. Oops. So, so how do we denote this? So basically, we still use these braces that we have here. So the braces indicate the set, and then the elements that you list in are the things that you put between the braces are the elements of the set. And we're basically going to use that same notation. So we have the brace X, and X is just going to represent some object or element or point in this set. And then often people use a vertical line. Um, and then there's going to be P of X. So this just represents any element in the set. And then this P of X is going to be like a proposition. So it's going to be a proposition or statement about X. And this is just stating that what this proposition is a proposition or statement about is it tells you or stating the properties or conditions an object, or an element. So an object must satisfy to belong to the set. And this could be a list of properties. It could really be anything you can imagine. So it could be, for example, um, the the property of, so P of X could be the proposition X is red. So then this set right here, so this set right here would be consists of all red things, or it could be P of X would be the proposition X is even, an even integer, say. And then so this set right here would consist of all the even integers. In that case, actually, you can list the even integers. It will be a subset. The even integers will be a subset of this set. But you can see that there are more concise ways of representing sets using this set builder notation. So you have this. So basically, how you read this then is how do you read this? It's read as the set of all X, and then you read this bar as such that um, P of X is true or is satisfied, or however you want to say it. So it's the set of all X such that P of X is true. And this set will consist of all and only those X that make the proposition true or the statement true. So with that in mind, we can define the rational numbers, and they're denoted as this. And what it consists of is all these fractions, as you would imagine. Rational numbers are fractions, such that P and Q. Here, I'm going to introduce some more notation. I'll explain it. Again, this is just review, so a lot of you probably see this. I know there's some people who have just joined the class, so I'm also going over some of this for the benefit of those who just joined the class. So of course you're free to skip this part. I'm sorry I didn't mention at this point, where I mean you're free to skip any of this. You don't have to watch this video at all, of course. So this the symbol right here just means this, like E looking symbol, just means in or belongs to. Um, of course, this is just the ampersand. This is just an. Q is non-zero. So these are the rational numbers. Oops. And again, so Q consists of all, or is the set of all P over Q, such that P and now, so now this is the proposition. This is the conditions or the properties that this element right here must satisfy. So what does this have to satisfy? Well, P and Q have to be integers, so they have to belong to the set of integers, and Q cannot be zero because you can't have division by zero. So that's how you read this set right here. So Q is the set of all fractions P over Q such that P and Q are integers and Q is non-zero. So that's how you define these. This set, and then finally, R can't. So real numbers are something we're so familiar with, but actually you need some quite a sophisticated mathematics to define the real numbers. So we're gonna kind of cheat. So the real numbers, and it's gonna feel like a cop out. But for our purposes, that's okay. So real numbers just consists of all rationals and irrational numbers. And then of course, rational is just means not rational. Yeah, or sorry, irrational means not rational. So it can't. So in other words, an irrational number is a number that doesn't belong to this set. It can't be written as in this form right here. And as I said, this is kind of cop out because like this doesn't really. This is like almost not even a definition really. Um, as I said, there's. I mean, really briefly, here's like one way of thinking about real numbers. So, there are obvious equations we can solve, like x plus 2 equals 0. You can just do your regular algebra and find that x equals 2. And look at that. It's actually the solution to this equation is a number we're familiar with. It's just an integer. Well, what about something like this? Let's say this. So the idea is we accept the existence of naturals, we accept the existence of integers, and we it's like we're like scaffolding this whole process. You start with the natural numbers, we know what they are, they're just counting numbers. You accept their existence as a given, and then from there you fill them in to get the integers. They're just the negatives of the naturals, and then you throw this element 0 in, and then from there you can build the rationals, and you just like scaffold this process, you just build them on top of each other, and then you can talk about equations over, say, the rationals. And this would be an equation over the rationals, for example. So this is a rational solution. In fact, um it's an integer solution. Every integer is a rational. But then when you come to an equation like this, of course we know how to solve this. You take the square root of both sides. But square root of 2, if you solve for this, you'll see that x is equal to plus or minus square root of 2. Square root of 2 is not rational. And it's actually non-trivial to prove. It's not it's not like it's easy as you think it is. And maybe I can go over the proof of that at some point. But basically how you define the real numbers is you consider all equations like this and you say, all right, I can't solve this using rational numbers, so I gotta just say there are these numbers which are solutions to these equations. And so you're filling in the gaps, basically. You have these equations which you can't solve. There are no rational number solutions, and we accept the existence of rational numbers. So what you do is you just, to get the real numbers, you fill in the blanks. Here's a blank. This is not an irrational number, so you have to fill in the blank. And then of course there's equations like x plus x squared is equal to x squared is equal to 3, and then you can solve for that, and that will give you plus or minus square root of 3. And again, you can show this one's even a little harder to show that this is not rational, but square root of 3 is not rational. So you kind of like, that's how one way of defining the real numbers is like you fill in the gaps. There's like these gaps corresponding to these equations right here, which have no rational solutions. So you just say let square root of 2 be that number that's such that it's a solution to this equation. So it's kind of ad hoc almost. It's like, wow, it's kind of weird to think that that's how you define one way to define Uh, real numbers, there are other ways to find real numbers. They're not so straightforward, but yeah, that's a very it's a much deeper topic than you would think about, than you would think, trying to define numbers. So yeah, so those are sets of real numbers. So that's what we covered. And then, as I said, we don't care about just numbers themselves. We don't care about sets alone. We want our sets to have structure. So let me just pull the book up so I don't have to, so I can get through this review more quickly. We want our numbers to have structure. So we can equip our set of numbers with operations, and these are operations are familiar with, addition and multiplication right here. And then they satisfy these properties. And then I gave the example of 2 by 2 matrices. It might, because it might seem to you like odd that we have to like specify these properties, but it turns out there are other sets of objects with their own operations on them that are like addition and like multiplication and satisfy these properties. And the example I gave was 2 by 2 matrices. You can define, a 2 by 2 matrix is just an array with 4 numbers in a box, and you can define addition and multiplication on these, and they have these properties right here. They have similar properties, so it's important to specify them because real numbers aren't the only numbers, or the set of real numbers isn't the only set with operations like these that satisfy these properties. Um, so yeah, so that's it's important to specify these properties: commutativity and associative and distributive property. So let's see, what else did we look at? Okay, so I mean, I didn't really talk about this, but let me just show you this really quickly. We have properties of fractions, and these are all familiar properties. Um, so I'll let you look at that for a little bit, or you can just pause it. So, um, I didn't really go over these kind of calculations. You can go over them yourself, this example. And of course, if you have trouble, you can meet with me. So all right, so here is sort of where we left off. Um, so you have this, I already introduced this set builder notation. Here's another example. You have the set A. You can just explicitly list the elements, but if you want to write it in set builder notation, you can use this. You can describe the set in this way. So it's A is the set of all x such that x is an integer, and x is between 0 and 7. Now, if you don't leave out this condition right here, if you leave out this condition right here that x is an integer, then you will be describing a much different set. You'll be describing an interval, which consists of an infinite number of numbers. So you would definitely not be describing this set, which just has a finite number of numbers. So it's important that you have not only that x is between 0 and 7, but that x is an integer. Otherwise, you're not describing this set right here. So both conditions are important. So it's important that you list all the conditions or properties which determine whether you belong to this set or not. Okay, so yes, the next thing we talked about was union and intersection. So again, so this just to emphasize the point I made earlier, you have the set of real numbers, they come with structure, addition, multiplication, and they're and they have these properties of associativity, commutativity, distributivity. But it's not true that, what's true is that there are other sets out there that have a structure like this. So if you look at the set of all sets, you can define the union of a set and you can find the intersection of a set. And these have properties that are like addition and multiplication. So let me just quickly define. We call this was called arithmetic of sets. So let me just write that down here. So arithmetic of sets. So given sets A and B, you can define their union and their intersection. The intersection, or sorry, let's start with the union. The union of A and B is defined to be the following. So it's going to be a new set. It's going to be built from this set. So I have to specify. It's not necessarily true that I can list the elements of A and B. For example, if we're talking about, like, say A was the rational numbers, I can't do that. I can't just explicitly list the elements. So there's no reason to think I can explicitly list the elements of their union. So I need to use set builder notation to define this set. So it's going to consist of all X such that X is a member of A or belongs to A, or X is a member of A or belongs to B, or both. This or in this case doesn't mean exclusively A or exclusively B. It could belong to both of them. So this is their union. So this is their union. So it's this new set built from these, and their oops, intersection is denoted as follows. And again, we're going to use set builder notation to define this. So the intersection is like this cap here. Let me draw it better. So, oops. All right, so let's try. Kind of like that. So it consists of all the X such that X is in A, and it's important that you have this and X is in B. So in this case, X has to belong to both A and B. So that's what makes these two sentences different. So make sure you know, I mean, it seems silly, but there is a huge difference between or and in mathematics. So that's how you define their intersection and their union. And we went over example. I won't go over it again, just to save time, but there's examples in the book. You can go over them. And then we looked at a specific type of set, was the interval. So you have these intervals, you have these open and closed intervals. This right here is the open interval. So notice it's defined by set builder notation. It's the most concise way to define it. And this is the closed interval, the one I highlighted. And then there's a bunch of variations. So here's the open interval, here is the closed interval. This is like a half open interval. These are half open intervals. These are infinite intervals from A to infinity, and then including or not including. Here's their set description, how they're defined as a set, and then here's graphical representations of those sets. And we did do this. We did represent some of these sets graphically. And we did some calculations like this. So I'll leave this to you to go back over if you want. And we define absolute value. Let's see. I did not write these properties down, but there's some. Well, I did write the first two properties down actually. So based on this definition right here, the absolute value, you can see this is actually an example of a function, even though we haven't talked about a function. It's a piecewise defined function. So you have the absolute value of A is defined to be A if A is non-negative, and negative A if A is negative. So you can see it's not too hard to argue or see that the absolute value of A is always a positive number. And that A and negative A have the same absolute value. And this one is not as maybe it's somewhat easy to see, but it's not as easy to prove. There's like a ton of cases to consider. And so it's kind of tedious to prove. 4 follows from 3 pretty easily, actually, because remember, division is defined in terms of multiplication. So yeah, let me prove that one. That one's not that hard to prove. So let's show that 3 implies, just call it 3 implies 4. So here's the proof. So if you assume that 3 is true, you can prove that 4 is true. So it's not that hard. So this can be written as this. And then based upon 3, we know that the absolute value splits over this product in this way. And then we can write, well, okay, I'm cheating in this one way. Um, Actually, there's one step. The one step is that B inverse, you can like kind of distribute, you can pull it out of the absolute value. That is one thing that you do have to argue. But assuming that is true also, you can write it like this. And that proves 4. There is this step right here going from here to here. You might wonder why is this true? Again, like this is not, it's a tedious to argue, so I won't argue, but you can argue with that. And then the last thing is the absolute value or the triangle inequality. This one's again not terribly difficult to prove. It can be, depending on how you prove it, tedious. This triangle inequality. All right, so that's enough of that. So let's move on to enough for review. Let's move on to 1.2, section 1.2. So this is oops. So this is 1.2, and this is exponents and radicals. So now that we've, in a sense, defined the real, well, we didn't really define the real numbers, but we talked about sets of real numbers. And as I said, we have these operations, these real numbers. We want to like further explore these operations and set up some more notation to make computations easier. So we're gonna look at we're gonna like just as we did with the sets, we kind of like built. We started with the natural numbers, then we went to the integers, and then the rationals. We like built upon each other like from a foundation. We're gonna do that with exponents. So we're gonna first look at integer exponents, then we're gonna look at negative exponents, and then work our way up to um, rational exponents. So this is very common trend in mathematics. You start at a foundation and you build up from there to more complicated ideas. So we're gonna look at integer exponents first. So we're gonna just set up a definition of integer exponents. So if A is any number, any real number, and then N is some natural number, 1, 2, 3, 4, any number that like that, counting number, then the nth power of A is defined as follows. Oh, I should say, so this right here means, so this is a different notation than an equal sign. This means definition. So this is means defined. It's basically like equal sign, but how this works, like if you take computer science courses, you'll see this notation a lot. It's to set up a definition. So what this symbol right here has no meaning, and now I'm going to um ascribe meaning to it. So that's what this, so it's not just an ordinary equals, that's going to be a definition, and it's going to be defined as follows. So this is going to be defined as follows. This. So the right hand side has meaning. I'm just going to multiply a by itself n times. So there's going to be n factors. And the left hand side doesn't have meaning, but now I am ascribing meaning to it. So it's very important to observe this distinction. And this right here just means I'm defining these symbols to mean this. So it's not quite saying that these things are equal. It doesn't imply that they're equal, but it's a stronger idea than equality. This is just saying I'm giving meaning to these symbols. And I should use it up here also, actually. So for example, this is a definition. This is not really an equation. This is these are definitions here. Let's see what else. Yeah, even these are definitions. So these are symbols. They have no meaning, and now I'm giving meaning to these symbols. Same thing with the rational numbers. So yeah, even with these actually. So yeah, so I might use that symbol just to just so you know what that means. When you see the colon and then the equal sign, that means that there's these string of symbols which don't have meaning, and now I'm assigning meaning to them. So that's what this means. So you a to the n raised to the nth power is defined to be this repeated product right here. A is called the base. And then n is called the exponent. And then there's just a really cheesy example in the book. So example one. So if you have, I don't know, let's say -3 to the fourth, it's gonna be -3 times -3 times -3 times -3. And if you do that out, you get 81. All right. So now, let's see. So now we want to extend this. So we want to want to extend definition to negative exponents. How do we make sense of that? So we know what it means to take a number and raise it to a positive number, but what about raising it to a negative number? So we just, well, how do we do that? Well, we just define um exponent exponentiation, or we define raising a number to a negative power in terms of this definition here. We like leverage this definition. So let me just explain how do we do that. So here we go. So definition. So if a is some real number but non-zero, and n is some positive integer, then a to the negative n. So this is a negative exponent right here. And how do we define that? Well, we're going to define it as follows. Okay. And so this we know how to deal with, right? We know how to compute this, and that gives us a way of computing this right here. So this is just uh, negative exponentiation is an extension of positive exponentiation. And then for convenience, we define a to the 0 to be 1, which is kind of weird. It turns out this is the right thing to do. It might seem odd at first. Why would I mean if the exponent is supposed to represent the number of times you multiply, why would a to the 0 be 1? So, but it turns out to be the right thing to do. It makes the arithmetic work out. This is the right thing to do. So there's a lot of times where there's a lot of things like this in mathematics where you encounter something and there's this convention that you set up, and it seems odd at first, but it's turns out to be the right thing to do. And that's literally the only explanation of these sort of peculiar things in mathematics like this, where you have something like a to the 0 is always 1. All right, so some more examples. So example one, or sorry, example two. So if you want to do -2 to the -3, well, by definition, right? By definition, it's going to be computed in this way. And now we've reduced the problem to something we already know how to deal with. And then when you do this computation right here, you're going to get 1 over -8, whoops. And then you can just put the negative in the front like that. So now, um, let me just pull this table up just to save some time. So um, again, the common theme in mathematics is you start with some very basic principles and some basic ideas or truths, and then you draw conclusions from that, or you draw conclusions from these definitions you set up. And so we have these rules or laws of exponents. So here's a bunch of them. So if you multiply a to the m times a to the n, then you can just compute it in this way right here. And there's some other ones about division, and none of these are very hard to prove. So these aren't very hard to prove. So let me prove a couple of them actually. So let me so you can see how mathematical proofs work or get an idea of how they work. So let's say we claim that this is true. So we're gonna just do a special case of m and n being positive. You can, because there are obviously a lot of cases. I'm not saying what m and n are. They could, m and n can be positive, negative. There could be any combination of them. So you have to consider all these cases, but we'll just deal with this case, and then the other cases you'll see if you go through them, they reduce to this special case that we're gonna consider. So if um m and m are positive, then by what does that mean by definition? Well, by definition, we can expand these two using that first definition. So this is be a to the m. So a to the m is going to be a times itself, m times, right? This is m times. And then a to the n is going to be a times itself, n times. Now, using the associative property of multiplication, we can just put all these together. And if you count the number of terms, what is it going to be? They're going to be m plus m terms, right? So all together, if you just drop the parentheses and put the terms together, they're going to be m plus n. You're going to do this multiplication m plus m times. But what is that by definition? By definition, that's a to the m plus n. And then you put your box to finish the proof. Of course, this is just a special case, and you can argue for the other cases pretty similarly. And then there's number two, if you have yeah, I won't go through all the rest of these proofs, but yeah. There's that table, so I encourage you to look at the table. Um oh, they do get actually okay, so I didn't realize. Okay, here, so let's write down let's look at their proofs. Um so there's number three. Actually, this proof's not necessary. Because if you know, actually, no, this is, yeah, it's okay. So you do have to consider these special cases. So for number three, you have to consider positive. So what does this mean? Well, remember, what is it if m and m are positive integers? What does this mean by definition? Well, a to the m is going to be a times itself m times, but then you're raising this whole block right here to the nth power. So what does raising this whole block to the nth power means? It means multiplying these blocks of m factors times itself n times. So if you have m blocks, if you have a block of m a's and you have n of those blocks, then you have n times n of those a's. So then by definition, that's going to be a to the m times m. And then as I said, you have these other cases where you have maybe they're both negative. You can just use the definition of negative exponents. Basically, everything will be flipped into 1 over these blocks. Then you have, so n is a positive integer, so you have ab to the nth power. So you have this number ab multiplied by itself n times. So here is what is an interesting point. You have to use the commutativity power to block the a's together. And of course, there are going to be n of them, and then you can block the b's together, and there will be n of them. Remember, I've talked about 2 by 2 matrices. You can put there's a way of defining multiplication on them. Well, when you multiply two matrices, say you have a matrix A and a matrix B, so it's a square with 4 numbers. Multiplication is not commutative generally. So this law does not hold for multiplication of matrices because it's not necessarily the case that you can group all the A's together and all the B's together. So it's important when you're talking about a set with some arithmetic on it or some operations that are like addition and multiplication, you got to be careful about what set you're talking about and what's the multiplication and addition in that case, because you might not have commutativity like you do with real numbers. So that's, when you do arithmetic on matrices, it gets kind of more complicated and sometimes more interesting actually, because you don't have this sort of law right here does not hold for necessarily always hold for matrices. All right, so let's work through some examples using these laws. All right, so this is example 4. Oh, sorry, no, it's 3. So this is part A, I guess. Yeah, okay. All right, let's just work through these quickly. So we have x raised to 2 different powers, but according to that law we proved, it's just the same thing as when you multiply x to 2 different powers or any number 2 different powers, you just add the exponents or you just add the powers. So it's gonna be x to the 11th. Now you have y to the 4th times y to the negative 7th. So in this case, we only proved it's a special case for m and m positive, but it does hold more generally for any positive or negative integers. So again, you just, in this case, you're going to add the powers or the exponents. So this would be 4 plus negative 7, so that's going to give you negative 3. And of course, you can write that as this if you want, doesn't matter. So number C is C to the 9th over C to the 5th. And according to the law, it's one of the exponents law. If you have a fraction like this where C raised to a power and then C raised to another power, you subtract the denominator from the numerator. That's how you simplify or compute this expression. So then you get 4. So D, so you have B to the 4th power raised to the 5th power. And when you have exponent of an exponent, you just multiply the exponents together. So it's in B to the 20th. So now we have E. 3x to the 3rd. This is the one we were just looking at, actually, the last one. And this law, the law really, as I said, requires that or really is based on the fact that addition or multiplication of real numbers is commutative. Again, if you're looking at matrices, this is not necessarily true. But because we're If it's commutative, it's fine. So when you have a product and you raise it to a power, you just raise each thing to the power. So this is going to be 3 to the third, and then x to the third, and then 3 to the third is 27 times x to the third. And then the last part is f, kind of x to the fifth. And it's the same thing as this law, actually. When you have, in this case, when you have a fraction raised to the power, you just raise the numerator and the denominator to that power separately. Sorry, this is not this example. I wrote it down, didn't write it down quite right. This is a 2 in the denominator. So let me see, this is supposed to be 2. So this is going to be x to the fifth over 2 to the fifth. And if you compute the denominator, it's going to be 32. So I computed these using that table I showed. So if you didn't quite follow those, just look through the examples again and look through the table again. And of course, you can come see me if you have questions. And of course, any questions that you have as you're watching this video, yeah, write them down and I can address them in class because I'm sure other people might have similar questions. So let's look at some more complicated expressions. So this is example 4a, part A. So it's going to be 2 times a to the third times b squared times 3ab to the fourth to the third. So now so there's not really much to do with this factor, but we have this other factor raised to the third power. So let's deal with that second factor first. So it's going to be 2a cubed b squared. So now in order to compute this, I have this product of 3 numbers, and the rule generalizes in the sense that if I raise this product of 3 numbers to the third power, I just raise each factor to the third power. So it doesn't matter how many factors you have in the parentheses, you just raise it to each one to the power on the outside. So you have 3 to the third, a to the third, and then you have b to the fourth to the third, okay? And then, so let's just copy down, let's keep these separated in parentheses, doesn't really matter. So this is the first factor still. Now let's simplify the other factors some more. So 3 to the third is going to be 27, a to the third, just keep it as a to the third. And then b to the fourth to the third, remember when you have an exponent to the exponent, you multiply the exponents. So 4 times 3 is going to be 12. And now we use the commutative property to move things around. So you have this 2 and this 27, you multiply those to get 54. You have this a to the third and a to the third. So what do? You add the exponents. So it's going to be a to the sixth. And then you have b to the second power and then b to the 12th power. When you multiply those two, you add the exponents. So you get b to the 14th. All right, let's look at one more example. So this is part B of the same example. So it's x over y to the third power. And then it's y squared x over z to the fourth power. So now you have x over y to the third power, so you raise the numerator and the denominator to the third power, so you get x to the third, y to the third. Now we're going to simplify the second fraction. So again, I have this fraction to the fourth power, so I just raise the numerator and the denominator to the fourth power. So this would be y squared x to the fourth power over z to the fourth power. And now I can simplify the numerator here. So I get, I have this product, so I raise each factor in the product to the fourth power. So y is going to be y squared to the fourth power. So I'm just going to multiply those powers together to get 8. And then x to the fourth over z to the fourth. Now I'm pretty much done. I just have 2 fractions and I need to multiply them. So how do you do that? Well, when you multiply 2 fractions, you multiply the numerator by the numerator. and the denominator by the denominator. So I have this x cubed. Well, let me just write it as one fraction first. X to the cube, x cubed times y to the eighth times x to the fourth over y cubed times x to the fourth. And then I can use commutative property of real numbers to put these two terms together. So when you multiply them, you add their exponents. So it's going to be x to the seventh, y to the eighth over y cubed, z to the fourth. And that's it. You're done there. All right. Let's look at another example. So this is with an example with negative exponents. Actually, let me see. Okay, so let me make a little observation about negative exponents first. That's not hard to prove. So note, if you have a over b, say to the negative nth power, and let's just say n is positive integer, then this negative, the negative has the effect of flipping the fraction. So this can be computed as this, like that. And then of course we know how to deal with this. This is just you, if you have a fraction to the power, you just raise the numerator or denominator to that power. So it's b to the nth over a to the nth. But the crucial part of the observation is this right here. When you have this negative here, it has the effect of flipping the numerator or the denominator. And that's not too hard to, you can prove that using the exponent laws. So if you don't care for that, just remember that. And we're going to use that in example 5. So example 5, let's see, let's just go over both example parts. So in this one, we have 6st to the negative fourth. And then we have 2s negative 2, s to the negative 2, and t squared. So when you have this negative, that means you just flip it and you flip it into either the numerator or the denominator. You put it in the opposite spot in a sense. So I have this t to the fourth, so that's going to go in the numerator and become t to t to the negative fourth. That's going to go in the denominator and become t to the fourth. And then I have this s to the negative 2. That's going to go into the numerator and become s to the positive 2. So I have s squared over here, up here. And then I have 2. So now I have in the denominator I have t squared. But don't forget, I flipped this into the denominator also to get t to the fourth. So I have 6 over 2. That can simplify to, I have a common factor of 2, so I can cancel that. So I have just 3 in the numerator. Now I have s. Really, I have s to the first power, right? That's s to the first power. So I add the 1 and the 2 to get s to the third power. In the denominator, I canceled that 2, so there's nothing there. And I have t squared times t to the fourth, so I gotta add those exponents together to get t to the sixth. All right, so now let's do b. So now we have y over 3z cubed. This is where that, to the negative second power. We did use this observation right here in part A. Maybe it didn't quite look like it, but we definitely did. But if it's definitely clear that we're going to use this observation again. In this case, so we have this negative 2. So first of all, the negative means we flip the fraction. It's going to be 3z cubed over y squared. So we did that, and now we have this fraction to the second power, so we raise the numerator and the denominator to the second power. So it's going to be 3 squared z to the, so I just All right, let me break it up into steps, just because there's a lot going on. And some people might need some steps, and that's perfectly fine. So it's gonna be 3z cubed squared, and then the denominator is gonna be y squared. And now we take that square and we distribute it over the products. We get 3 squared z cubed squared over y squared. And then I just use then I just square each thing. So we get 9. And then z to the third to the cube means you multiply the 3 and the 2 to get 6 over y squared. All right, I need to pause for a second. All right, so the next thing we're going to look at are radicals. Okay, so radical. Before we introduce the more general idea of a radical, let's recall what a square root means. So if we have, so we know that the square root of 4 equals 2 because when you square 2, you get 4. Okay. And more generally, the square root of a equals b means that b squared is equal to a, and b is some positive number. So that's what it means. So in other words, the square root of a is that number is equal to that number such that when you square it, you get the thing under the radical symbol. So the reason why the square root of 4 is equal to 2 is because 2 is that number such that when you square it, you get 4, which is the number under the radical. So that's how square root works. And of course, it's a little observation, since a is equal to b squared is positive, this only makes sense when itself is positive. So that's why we get this rule about that's why we get this rule that it only makes sense to take square root of positive numbers. Of course, unless you go, or non-negative numbers, you can take the square root of 0 also. And that's not true, of course, when you do the complex analysis or when you deal with complex numbers. So from this idea, then we can define the nth root. So and it's just it works off this right here, this definition, very analogously. So let me write down that definition. So here's a definition. So we take n to be any positive integer, then the nth root of a, or I should say, it's not just the nth root. We're talking about the so-called the principal nth root, the positive nth root. So the principal, it's not going to matter a whole lot, but let's just be technical. It's always a good idea to be technical and precise with your definitions. So the principal nth root of a is defined as follows. So I can talk about taking the nth root of a, and how do you do it? This formula or this definition I'm setting up tells you how to find it, actually. So this equation right here means that when you take b and raise it to the nth power, you get a. So to find this nth root of a, you have to find a number such that when you raise it to the nth power, you get the thing under the nth root. And that's basically, as I said, it's a direct generalization of this right here. and of course this right here. So again, this definition right here, or even this definition right here, gives you a prescription on how to find nth roots. So it's more or less just guessing. To find the nth root, you have to guess and then check. There's not a really a nice way to calculate it. So if you want to, so for example, let's see. Oh, the definition is not done. So yes, this right here gives you a way or of calculating. Or it tells you that you need to guess and then check um, to find the nth root of a given number. And of course, if n is not just a positive integer, but n is even, um, we must have a positive and b positive. All right, so let's look. So for example, let's see what kind of examples do they have here. Actually, it's not even officially an example. So, anyways, they don't list it as an example in the book, but you can take the fourth root of 81, and that's going to be 3. And this really you just find by guessing. And so the reason why it's 3 is because when you take 3 and raise it to the fourth power, you get 81. And of course, 3 is a positive number. For another example, you can take the cube root, the third root of -8, and that's going to be equal to -2. And again, this is just found by guessing. And the reason why it's this cube root right here is equal to -2 is because when you take -2 and cube it, or raise it to the third power, you get -8. So yeah, it's just a matter of just guessing and checking. So we have some properties. So let me show you these properties from the book. I won't write them all down, but you have these properties that are, yeah, you can, as always in mathematics, everything follows from the definition. So all of these will follow from this definition right here, and the one which is the one I wrote down. Um, but it's usually it's kind of tedious to verify these, but so you can just accept these as true, or if you want to know, of course, if you want to know why they're true, you feel free to like talk with me during office hours or whatever, and we can try to figure out why these are true. All right, so let's look at an example using these properties of the nth root. So this is example 9 in the book, part A. So we want to take the cube root of x to the fourth. So the easiest way to do this is if you have like say x to some number and you're taking the cube root, is you want to if you want to remove as many multiples of 3 from that number that's the exponent as possible. In this case, we can just remove one multiple. So 4 can be written as x to the third plus 1. And then if, sorry, the 4 can be written as 3 plus 1. So it's x to the 3 plus 1. And then, of course, using properties of exponents, we can write it in this way. Oops. And then now I have the cube root of a product, so this distributes the cube root distributes, or more generally the nth root distributes over products. Now this doesn't really simplify anything any at all, so we'll just leave it that way. But this right here is going to be equal to x, because well, it's kind of trivial. I won't even write it down. Why is it equal to x? Well, because when you raise x to the third power, you get the thing under the cube root. So that's why that's going to be equal to just x. So this simplifies as follows. All right, so that's part A. Now let's look at part B. So now I'm going to take the fourth root of 81 x to the fourth times x to the fourth times y to, oh sorry, it's x to the eighth times y to the fourth. Again, so I have a product, in this case it's three numbers, but still, as long as there's a finite number of terms in the product, I can distribute that fourth root, or more generally the nth root, over all three numbers. So this is going to be equal to 481 times, sorry, the fourth root of 81 times the fourth root of x to the eighth times the fourth root of y to the fourth. So the fourth root of 81 is going to be 3, because when you raise 3 to the fourth power, you get 81. This right here is going to be x squared, because when you raise x squared to the fourth power, you get x to the eighth. So this right here is equal to x squared, because let me see. Let me actually just write all of those down. So this right here is equal to 3, and then that's because 3 to the fourth equals 81. This right here is equal to x squared, because x squared to the fourth is equal to x to the eighth. And then this right here is just simply equal to y, because when you raise y to the fourth, you get y to the fourth. So then this simplifies to 3 times x squared times well, I should be careful now. If you don't know x, the y itself is positive or negative, it's actually going to be equal to absolute value, because you don't want you're the nth root of the nth root for when n is an even number, so like say 4, cannot be negative, so you have to put the absolute values on there. All right, let's see. All right, I guess we'll just do example 10 also. So this is an example on combining radicals. So we have part A, we have 32 plus more, it's not really combining, I guess, sort of, I guess. It's more or less simplifying. So we want to just simplify this as much as possible. We want to reduce these numbers as much as possible. So 32 can be written as 16 times 2, and then 200 can be written as 100 times 2. So now we'll use the fact that the root distributes over the product, write it like this, and then write this other term like this. Now the root of square root of 2, you can't simplify that any further, but these two numbers you can. So this first one is going to be equal to 4, because when you square 4, you get 16. So it's going to be 4 times root 2. And then this is going to be square root of 100 is going to be equal to 100, because when you square 100, when you square 10, so the square root of 100 is going to be 10, because when you square it, you get 100. So it's going to be 1. It's going to be 10 times root 2. And then this is you can combine these, because like this square root is the same as this, and then this is just the coefficient. So you can combine these to get 14 square root of 2. One way to see that is as follows. You have this common factor right here, so you can factor that out. So you get 4 plus 10 root 2. And then you combine the 4 and the 10, and that's why you get 14 root 2. That's just one way to see it. I think that's really honestly the best way to see it. All right. And then I guess all right. Yeah, I guess we'll just do B also. Let's just do all of them. So this is part B, and B is going to be a variable in this problem, so B is, but we're going to assume it's positive. So if it's positive, then we can calculate or we can simplify the following as follows. So we can simplify this as follows. So we're going to take, for this first term, we're going to take the square root of the product. It's going to be the product of the square roots. And then for this, b cubed, you want to take as much, you want to break this 3 down into like some multiple of 2 and then something else. You want to do that as much as you possibly can. In this case, we can only do it once, so it's going to be b to the squared times b. So square root of 25 is going to be 5, root 5. And then, well, I'll just distribute this and then simplify. So the square root of b squared is going to be, technically, it will be absolute value of b, right? This first part right here, this term right here is going to be the absolute value of b. But since we're assuming b is positive, it doesn't. We can just drop the absolute value, so we get this. So this would be square root of b times, or b times the square root of b, and then again, the 5 and the b, they're like coefficients of the square root of 5, so you can add them together. So you get 5 minus b times the square root of 5, or you can just think, another way of thinking about it is this is a common term, and the thing and the square brackets underlined with square brackets are common terms, so you can factor them out to get this. And then for C, this is the last part. Let's see, I lost it for a second. Okay. So now what we have for this part is the square root of 49. Oops. Times x squared minus plus 49. And our goal is to simplify this as much as possible. So we have a common factor of 49. So I can factor that out. And then I have a square root of a product, so it becomes the product of the square roots. Now this I can't really do anything with, so I'll just leave it alone. But this I can simplify. So it turns out the square root of 49 is 7, because when you square 7, when you multiply 7 times 7, you get 49. So this is going to be 7 times x squared plus 1. All right, so that's for that, all for that. Now, so now that we can take integer exponents and we can take radicals, we can define, again, we're leveraging from previous facts I have, we're scaffolding, based on things we've already find and things we already proved about these things. So now that we have know how to compute integer exponents and radicals, we can talk about rational exponents. And it's just a obvious extension or generalization of everything we've been doing. So I'm just going to write down the definition. There's not going to be any motivating example. It's going to be pretty straightforward what you need to do. So for any rational number, or I guess just saying rational exponent, m over n in lowest terms, meaning m and n don't have any common factors. Of course, m and n are integers, and let's say n is positive. We define a to the m over nth power. So this is our rational exponent. So how do we define it? So these are symbols, they don't currently have any meaning, and now we're going to assign meaning to them. So what's the meaning? Well, the meaning is that you first take the nth root of a, and then you raise that whole thing to the mth power. Or equivalently, you can say it's a to the m, a to the m over nth power is the same thing as taking the nth root of a to the a to the mth power, sorry. And if n is even, we require that a be non-negative. All right, so let's just look at a couple examples. So this is example 11, and we'll just do part B. So we want to compute a to the 2/3. So by definition, that's going to be you take the cube root of 8 and then you square the whole result. So first of all, the cube root of 8 is going to be 2, right? Because when you take 2 and raise it to the third power, you get 8, which is under the cube root. So this is going to be 2 squared. And now we're just doing an integer exponent. So, and we already know how to compute with those. So this is going to be 4. All right, let's move on to example 12. So let's do A. So we have a to the 1/3 times a to the 7/3. So the rules for the same rules that we've been using about adding these exponents applies for rational exponents too. You can prove that those same laws. So let me pull this table up. So this right here. So even though in this table we were restricting m and n to be integers now, it turns out all these same rules right here apply even if m and n are rational numbers. So we've kind of like generalized these laws right here to apply even for m and n to be rational numbers. Okay, so with that in mind, we can compute this pretty easily then. Let me just get this back to where it was. Okay. So this will become a to the 1/3 plus 7/3. And then now we just add the fractions to get 8 over a to the 8/3 power. All right, let's look at B. So we have a to the 2/5 times a to the 7/5 over a to the 3/5. So first of all, you can just you can deal with the numerator first, and we know how to deal with that. So it's gonna be a to the 2/5 plus 7/5, and then divided by a to the 3/5. So we'll simplify this exponent right here to get a to the 9/5 over a to the 3/5. And now, since we have this division right here, this means we subtract the power in the bottom, the denominator from the power in the numerator. So it's going to be a to the 9/5 minus 3/5. And then that simplifies to a to the 6/5. All right, part C. So we have in part C 2 times a cubed times b to the 4th raised to the 3/2. So again, we can the law about taking a product to a power applies even if that power or that exponent is a rational number. So I can, in a sense, still just distribute this power over each term in this product. So it's going to be 2 to the 3 halves, a to the 3 raised to the 3 halves, times b to the 4th raised to the 3 halves. All right, so now this right here is going to be, by definition, it's going to be, sorry, it's going to be square root of 2. I guess the easiest way to see that is that we're taking the square root of 2 to the third, and then this remember when you have a power to a power, you multiply this power. So it's going to be 3 times 3 halves. So it's going to be 9 halves. And then this is going to be, it's power to a power. So it's 4 times 3 halves. So it's going to be 12 over 2. Now the 2 cubed can be written as 2 squared times 2. So yeah, let me just write that out. So this can be written as 2 squared times 2. 8 to the 9 halves just stays the way it is. But now we have 12 over 6. So that can be written as b to the 6th power. And now this right here, this first term is can be written as 2 times root 2 times a to the 9 halves times b to the 6th power. All right, so the last part, this is part D to this example. We have two fractions we're multiplying, so it's 2 to the x raised to the 3/4 over y to the 1/3, and this whole fraction is raised to the third power times y to the 4th over x to the negative 1/2. So let's just deal with this because we first, because we have this fraction to the third power, and actually see we have this x in the 1/2 to the negative 1/2, so that means you flip that into the numerator. So we have this this third power, so I can just take the third power of the numerator and the denominator separately. And then this will be y to the 1/3 cubed. And then this will be y to the 4th times x to the 1/2. And now I have this cube. I'm taking I'm cubing this product, so it's gonna be 2 to the 3rd, and then x. So now I have x to the 3/4 raised to the third power, so I multiply the exponents to get 9 over 4. And then the denominator, I have 1/3, y to the 1/3 raised to the third, so I multiply the exponents, and that just cancels to give me y. And then of course this is all times y to the 4th, x to the 1/2. The 2 to the third becomes 8. Now I can multiply this because this is really y to the 4th, x to the 1/2 over 1. So I can multiply numerator by numerator and denominator by denominator to get this. And then I can cancel some terms. So I have a factor of y in the numerator and the denominator, so those cancel. And then I have this x to the 9/4 and x to the 1/2. So I can add I can add those powers. So I have 8x to the 9/4 plus 1/2. Then I'm just gonna have y cubed, and there's gonna be no denominator now. Oops. So now I just have one last step, and I need to add these fractions to get the exponent. And so 1/2 can be written as 2/4. So then I have 9/4 plus 2/4. So it's going to be 11/4 times y to the third. So 8 times x to the 11 over 4 power times y cubed. All right. Let's see. All right. I think that's it. I think that's enough for today. So just work through this, write down any questions you have, and on Wednesday we can just go over any questions that anyone has about this virtual lecture.